Thank you, Roya. Well, good afternoon, ladies and gentlemen. This is John Clark. For our first colloquium of 2021, I'm delighted to introduce our own Professor Yasunori Nomura. Yasunori was born in Kanagawa in Japan and received his PhD from the University of Tokyo in 2000, where he held a fellowship of the Japan Society for the Promotion of Science. He moved to Berkeley as a Miller Research Fellow from 2000 to 2002, and in 2002 became an Associate Research Scientist at Fermi National Lab. He moved back to Berkeley to join our faculty in 2003. Among his awards and honors, he received a Department of Energy Outstanding Junior Investigator Award in 2004 and an Alfred P. Sloan Research Fellowship in 2005. He was a Hellman Fellow in 2005 also, and then a Simons Fellow in 2012. And in 2017, he was elected as a Fellow of the American Physical Society. Just as a small comment, many of you would like to ask questions, and if so, would you please put them in the chat on Zoom, and then we will respond to the questions at the end of the colloquium. So please join me in welcoming Professor Nomura. His title is on his screen. Welcome.
Great. Thank you, John, for introduction. I think everything is okay and people hear me. Okay. Yeah, okay, great. And it's great and good to see you all at the beginning of the year. And hopefully this year is better than the previous one, and we can see with each other at some point in the middle of the year. Okay. So today I'm talking about some recent progress in quantum gravity and brought by studying black hole physics. And so as you probably know, the problem itself is not recent, it's an old one. So these recent progress certainly build on previous studies and what we previously learned. So I'm first explaining what's this black hole physics, what's the problem, and so on. And many of the things, some of you may have already heard that, and then towards the end of the lecture, or like last half, and I start talking about some recent progress about it. Okay. So somehow my cursor is gone. I think you see a razor pointer right now, right? Okay. Okay, and my face seems to be black, but I think it doesn't matter. People are not interested in seeing that. All right, great. So one of the major problems in current physics is concerning two pillars of modern physics. We know it's quantum mechanics and general relativity. In particular, the problem is that the structures of these two theories are so different that they don't get along well. We don't have some pretty simple unified theory which is reduced to quantum mechanics or general relativity in certain limits. It's not like that. And so that's unifying these quantum mechanics and general relativity is a holy grail of theoretical physics. But in usual circumstances, we don't have too much problem. That's why we can live with the current situation. For example, if you think about some microscopic physics, the force between proton and electron, okay? And let's think about the gravitational force and electromagnetic force, both goes like 1 over r squared. So the ratio is constant as a function of the distance. And then this ratio, if you compute it, the gravity is about 40 orders of magnitude smaller than electromagnetism. No experiment can have a 40 order of magnitude sensitivity. So in terms of talking about, say, particle physics and nuclear physics, microscopic physics, gravity is almost completely negligible. Okay? And you say, oh, well, gravity is important. Of course, in astrophysics and cosmology, gravity is a dominant force. But those are about the macroscopic physics. And let's think about the macroscopic two bodies made out of a lot of constituents, say N, big N, that's much bigger, like Avogadro number and so on. And imagine it, let's consider quantum effect, interference effect of these two macroscopic body. And if the probability of each particle composing this object, the probability of interference is epsilon, then in order for these two objects to interfere at the same time is at epsilon to the n, that's essentially zero. Okay? So the quantum effect is really unimportant in the macroscopic distance. And because of those things, you can just patchwork these two theories. And in one regime where quantum mechanics is so crucial, you can treat gravity as a perturbation, at the very least, and the vice versa. So in a practical, usual circumstances, we don't have a problem. But that doesn't mean that we don't have a theoretical problem unifying these two. So interesting thing happens in, of course, extreme circumstances. And a good example is, of course, when the object moves very fast in Newtonian mechanics, then, of course, special relativistic effect become important. You will see some new effect, which cannot be captured by just all theories. And for gravity, one strange thing that happens is at short distance. Imagine that we consider some process which occurs in higher and higher and higher energies. And because energy is mass due to Einstein equal mc squared, so the gravity becomes strong. Yeah? So at the high energies, the gravity becomes stronger, stronger, stronger compared with the other forces. And at some high energies, which is 10 to the 16 TeV, which is about 15 order of magnitude bigger than the current highest energy we achieved at the collider on the Earth, that's about 10 TeV. The 15 order of magnitude larger energies, gravity become as important as the other forces. Okay? And in quantum mechanics, energy or momentum is essentially inverse of the length because of the uncertainty principle, delta T, delta P, delta X, H bar, which I take to be 1. H bar and C is 1 in my slides from now on. So the length scale, very high energy length scale corresponds to short distance. And in fact, when the gravity becomes as important as the other force, that's about 10 to the minus 33 centimeters, which is very, very, very small. Okay? But at that scale, in fact, the theory loses control. And the theory we know to describe quantum mechanics in special relativistic setup is called quantum field theory. But we know that at this short distance, quantum field theory loses theoretical control. You can't, you see that a lot of formal divergences, and if you want to treat those, and then you lose the predictivity. But a lot of evidence says that the right theory to deal with this short distance physics is what is called string theory. And we already know that string theory contains gravity and contains quantum mechanics, or string theory is in the quantum mechanics, and this theoretical controllability is recovered. But on the other hand, and yet this formulation of string theory, the current formulation of string theory is essentially perturbative, okay? Not completely, but roughly perturbative. And there is certain problem that this current formulation of string theory, even if string theory is in the end correct, cannot directly address. That's the theme of today's talk, which is related with the physics of black holes. Okay, so the black holes. And this unusual situation, which we want to focus on to see some breakdown of the patchwork between quantum mechanics and general relativity. This unusual situation doesn't happen, not necessarily just a short distance, as short as 10 to the minus 33 centimeter. In some case, even in macroscopic systems. Okay? The black holes, how the black hole occurs. The black hole is an object which forms at the end of the evolution of the star. If you think about the star lives long, right? Billion years or 10 billion years. That's because in regular stars, the nuclear burning at the center produces pressure upwards. That's balancing with a gravitational force, which try to collapse the matter. Okay? But when the nuclear materials are all used up, if the mass of the object is sufficiently big, and then nothing to stop this gravitational collapse, and the material is really collapsing into kind of central point. Okay? At the level of general relativity, it's actually going to a point. So that has huge mass density so that the escape velocity exceeds the speed of light. And nothing can move faster than speed of light. So that means if you send some light rays from the center, and they can go up to a certain height, and you cannot go more than that. So you have that kind of some fixed surface, which is called horizon. So nothing inside that can go out of it, okay? But remember that this horizon is kind of middle of nowhere. It's just simply the surface. We just call this at the highest place we can go as a horizon. There is no material surface according to general relativity. Material is all at the center, okay? So horizon is some maximum height that any signal can go from this central point, okay? So that's the horizon. And yet, if you view this system called black hole from outside, then because nothing inside the horizon can escape, the horizon looks like completely black. Yeah? Even light cannot come out from horizon. So the horizon looks like just a surface in that sense, yeah? From outside point of view. And then this black hole has only properties, it's called no-hair theorem, properties like of mass or charge or angular momentum, like these macroscopic properties. Because all these details of the surface of the material which form the black hole is at the center, yeah? Really. So what's the material it's formed? Is that iron? Is that something else? Is that all these detailed information is supposed to be at the center. So this surface looks like just carrying only information like mass or charge or angular momentum, these things. That's called no-hair theorem. It doesn't have, black hole doesn't have detailed properties. Yeah? But is it true? What are the quantum properties of this black hole? Yeah, this is a classical general relativistic description, but we want to talk about some possible unification between general relativity and quantum mechanics. So let's talk about some quantum mechanical properties of the black hole. Yeah. Of course, we don't have a complete theory unifying it. That would be our goal. So the argument, discussion should be argument. Okay. So that's our next topic, black hole thermodynamics. To address this issue of say what's the quantum mechanics of the black hole, historically there was a big hint was obtained by thinking about some third pillar of modern physics, that's thermodynamics. Yeah? The thermodynamics is applicable to any system. Okay? It's system independent theory, any system for all practical purposes. And it says that the entropy of the system, entropy being given some macroscopic specification of the system, how many possible microstate configuration you can have. Let's think about some 20 degrees centigrade in the air of the room, keeping that temperature and pressure, how much microscopic configuration of atom you can consider. And if you take the logarithm of that number, and then that's called entropy. And that number should keep increasing, or at least not decreasing as a function of time. Okay, so that's the law of thermodynamics. But now let's think about this thermodynamics of the black hole. Suppose you have a black hole, and then you have some box with the gas inside, and the gas has entropy. Okay. Now you throw into the black hole, and the black hole absorbs it. It becomes slightly bigger black hole. But no-hair theorem means that there is no information other than the mass. So entropy is essentially zero. Okay. You don't have any detailed information or detailed microscopic configuration, apparently. So if this is right, then in black hole physics, the thermodynamics would not apply because entropy simply decreased by throwing in entropy into the black hole. But it was known even back then that the black hole had peculiar properties due to Hawking, and that's called area theorem. So if you think about two black holes, of the area of the horizon, okay, area of the horizon to be A1 and then A2. Think about the two black holes. And then black hole merges. And then what happens? Of course, it becomes single bigger black hole. Okay? Let's call area of that big black hole, final state black hole, to be A3. Again, area of the horizon, okay, as viewed from exterior. And these areas always non-decreasing. So in this case, A3 must be equal to or bigger than A1 and A2, the sum of the A1 and A2, always. this is almost looking like entropy, okay? And the proposal was a great proposal. And one of the major progress, I would say, in late 20th centuries was this Bekenstein's proposal that he proposed that the entropy of the black hole is in fact is proportional to its horizon area, okay? And remember, and then in fact, this horizon area in unit of Planck length. Of course, the area has a length square and it's in unit of Planck length. Remember, the Planck length was 10 to the minus 33 centimeter. It's very small. So this is an area measured in very, very tiny unit. So that means that entropy of the black hole is actually huge. It's not like no scale, no hair and zero. It's completely opposite way. It's huge, super hyperentropic system, okay? And if you compare like a number, for example, imagine that you have a solar mass black hole that has entropy 10 to the 78 roughly, okay? And while the entropy of the sun is much smaller, which 10 to the like 60s, okay? So that means it has the same mass black hole has 78 orders of magnitude bigger entropy than the sun. And the number of possible configuration is exponential of that. Remember, the entropy is a log of possible state you can take, micro state you can take. So it's a huge micro state associated with a black hole. Okay? So that's the consequence of this proposal. And indeed, not just Bekenstein just say this, and he could show that in the case of this previous example of throwing in some matter or radiation into the black hole, and then some of the previous initial black hole's area in unit of Newton's constant or Planck length square, and plus some initial matter, and the final state area of the final state black hole is always bigger than the sum of these this and area in Planck units in this thing. Okay? So total entropy still increases or non-decreasing as a function. So that's all great. So in fact, the thermodynamics, which we think the third pillar of the modern physics is upholds in black hole physics. But then, you know, somebody goes saying, oh, it doesn't make sense. It doesn't make sense because if that's the case, the area of the black hole in short-shield black hole is proportional to mass square. And G Newton and then H bar and C, of course you have to make a dimension correct, but it's a finite entropy you have. And then energy of that black hole is mass itself, it's M. And thermodynamics tells us that if you take a derivative of entropy with respect to energy, that must give inverse temperature. And according to this proposal, entropy is a finite, and then E is a finite quantity. If you take derivative, it should have a finite temperature. Doesn't the black hole just only absorb the stuff? If it has a temperature, it has to be radiating. And that's motivated Hawking to compute his famous computation, including quantum mechanical effect in general relativity. Okay. And you know the famous story, this is so famous, so that I won't go in detail, but his calculation, again, was not complete quantum gravity calculation. Right? We can't do that because we don't have theory. That's still the problem of the current physics, okay? Unifying theory of general relativity and quantum mechanics. But he could still get the answer by clever patching of general relativity and quantum mechanics. And in the end, his claim is the following. If the horizon of the black hole is smooth, and then if you include the quantum mechanical effect, and then that must mean that the surface called horizon must radiate corresponding to some temperature which he computed that is exactly this satisfied Bekenstein relation. Temperature it's obtained by this Bekenstein relation. In fact, historically, this fixed the coefficient of that entropy, but it's exactly the right temperature we have. Okay, that's the statement. So what's this statement, horizon is smooth? Okay, let's just elaborate a little bit about this statement. If the horizon is smooth, then you get radiation. What's the meaning of that horizon is smooth? Okay. So in general relativity, if you look at the black hole from exterior, and then you have somebody sitting here and counting time in 0 sec and 1 sec, and the body is falling in. Okay, that's what the body is falling in. And then because of the gravitational time delay, for the outside observer, the body looks like becoming smaller, slower and slower and slower as approaches the horizon, and never inside the horizon. Okay? Because of the huge gravitational effect leads to huge redshift effect. But on the other hand, the clock that object carries, okay, is really not the same as an object clock carried by a distant observer, famous relativistic effect. So it's 1 sec, 1 sec, but 2 sec, 1.9, 3 sec, 1.99, 1.999, 1.9999. So as approach to the horizon, it just only takes a finite time for from the clock's the point of view of the clock of falling observer, actually. Okay? So it was like this animation was my state of the art of the animation, which is okay. People just having funky animations, but not for me. But anyway, so that's the situation. So from the point of view of the really falling object, then in fact, it's nothing happening. Yeah, it's just really, when it reaches horizon, it's just 2 seconds, and 3 and 4, okay? Just smoothly passing. And if that statement, that's the prediction of general relativity, by the way, okay? If that's correct, namely general relativity is correct, that, and then including quantum effect, in fact, we have to get some radiation as viewed from exterior or far away person. Far away person view horizon as anything, the Hawking radiation. Okay, so that's the statement. And so that established like black hole is actually somewhat dynamic object. Okay? That's great. It's consistent. Really, the third pillar is still consistent, even existence of the black hole. And that's dramatic because remember, horizon itself, and entropy is proportional to horizon. Horizon itself is kind of middle of nowhere for the spacetime. Okay, it's not really at the center where the material exists. So that surface seems to carry entropy, meaning that spacetime itself seems to have degrees of freedom, huge number of degrees of freedom, because black hole has a huge entropy. Okay, so that's the implication of this discovery. It's a few things. Spacetime actually composed of some material, whatever that is. Okay, it's probably not the usual material. And then take the logarithm of the possible configuration of those material constituents of spacetime, then it gives area law, okay, of the black hole. Okay, that's so far it's great, but there was a problem. And remember, this Hawking did the patchwork of the general relativity and the quantum mechanics. But he did the patchwork in the regime everybody believed that his patchwork is correct. Not like extending in some, in the regime, his patchwork must be correct. And assuming his patchwork is correct, and then what he found that the radiation from the black hole, it just depends on the mass because it's no hair theorem. So imagine that you form the black hole collapsing some disk, okay, of some mass m, and then form the black hole, and then it evaporates and become a Hawking radiation. Or you collapse some different thing, it's just a shell, book shell or whatever, and then with the same mass, and then you form the black hole. And then black hole is the same because it's the same mass, and then final state Hawking radiation is also same, exactly same. That's the problem. It's information about the initial state is lost. You may think that this is not the problem. Information is lost. If calculation says that, and then it's that. Yeah, but this is a huge issue and a huge problem. We have never seen this kind of a situation in history of physics. In physics, say Newtonian equation motion, or even Schrödinger equation in quantum mechanics. So all differential equations, it's deterministic equations. So if you have perfect knowledge about your state at a given time, then you can solve future by solving equation motion, or you can solve backwards in time. Then you can see the past configuration, like a ball is, just throwing a ball, and then you can just solve it completely if you have perfect knowledge. Okay, and that's why you could do physics. But this is telling you that, in fact, the time evolution is not even one-to-one. Okay. So if you reverse in time, then you see how dramatic this statement is. Same states evolve into different final states if you reverse in time. Okay? The statement is as dramatic as that. Then you can't do science. Okay? You have perfect knowledge about the current state. You can predict in this case, it's past states, yeah, or future states. So it's not like somebody says, oh, information loss, who cares? No, we care. It's a big issue. That was called famous black hole information problem, at least in original form. So how to address this? This looks so weird, and then this one-to-one, evolution is in fact one of the principles of quantum mechanics called unitarity. You may think that it's probabilistic, right? Quantum mechanics is probabilistic. If you do the E plus A minus scattering, you sometimes see EE, you sometimes see muon, you sometimes see tau tau. Therefore, it's not deterministic anyway. That's not correct. Yeah? This is a fundamental state. So E plus A minus initial state, in that case, is just simply going into superposition of EE and mu mu and tau tau and z z. We can even compute the coefficients of these superposition. That's called S matrix elements. And then when you interact with this superposition, you feel sometimes as EE, you feel sometimes mu mu. But if you include U as a state, then evolution of that state is still unitary. It's one-to-one deterministic. And this is different from that. It's saying fundamentally non-deterministic. Yeah, that's a huge problem. So how to address this problem? In fact, the answer or key clue to address this problem, in fact, came from black hole physics itself. That's all holography. You may have heard. So recall that entropy of the black hole is proportional to area of the horizon. That's strange, okay? Because black hole is expected to be the final state of any evolution. If you do the collapse and so on, the final state is a black hole. So that means black hole is highest entropic object. You can think in that space-time region. Now, if that's the case, what we expect is that entropy goes like volume. Why? Because, for example, if you imagine that the space-time or space is composed of some lattice or something with a Planck distance, like this, okay? Because Planck distance, this is where the space-time picture is expected to be broken down, expected to break down, okay? So it's natural to imagine that the space-time is actually lattice of the Planck size. Then the number of configuration is either you put particle or not to put particle, for example, and then it's a 2 to the volume in Planck units. And if you take a logarithm, that's a volume in Planck units, which is much, 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 much larger than area in Planck units. Remember, Planck's length is just only 10 to the minus 33 centimeter. Yeah? So this is the power 2, this is the power 3. But this black hole entropy, Bekenstein and Hawking entropy, says that the maximum entropy you can host, this region can host, is just the area. Okay? Much smaller than what you expect from the naive view that you have actually space down to the Planck length. That's a fake, that's an illusion. You may think it doesn't make sense, you just put the material or you put the particle in each lattice site. What's wrong with that? It's wrong because if you start putting the material in each site, way before filling up these lattice sites, black hole forms. And if you add one more particle, it simply makes black hole bigger. Okay? So it's not the filling in. So these picture that you have a space, concept of space down to Planck length is actually a complete illusion. Yeah? You don't have that. Okay? That's a dramatic thing. So this implies that, in fact, actual true degrees of freedom, number of degrees of freedom, seems to be one dimension less than what we naively think as a space-time is. So we think we live in a 3+1 dimensional space-time with a 3-dimensional space, x, y, z, and time. But actually, the degrees of freedom, the amount of degrees of freedom we have correspond to 2-dimensional space. Because of this, it's just a volume, it's down to area. So if this is right, we must be able to, or at least it's natural to expect that we have a formulation of quantum gravity in one less dimension than what you actually perceive in regular life. Okay? And this phenomenon is called holography. Sounds crazy? Yes, it sounds crazy. It should sound crazy. It's completely crazy. But in 1997, it was shown, although in certain limited case, that in fact the quantum gravity obeys this principle of this phenomenon of holography. In particular, what Marcasena shows that in certain spacetimes called asymptotically ADS, anti-de Sitter, it's just a class of spacetime. In that class of spacetime, let's imagine that you have like a 2+1 dimensional asymptotically ADS spacetime. And then he showed that this theory, namely theory with gravity in this case, 3 dimension, is equivalent with the theory without gravity in 1+1 dimension. It's one less. That's precisely what the holography of Bekenstein-Hawking entropy has suggested. And he figured out, in certain cases, even map between the quantity of the gravitational theory and the quantity of non-gravitational theory. It's a 1-to-1 mathematical map. Okay? There's something called, say, curvature of the space-time and so on, a lot of this area of certain surface, and those geometric concepts, it's just translated into entanglement or some entropy or some quantum information quantity in one less dimension. So if we ourselves are living as a subsystem of this thing, and then in fact we are subsystem of the theory without gravity in 2+1 dimension. But then we interact with a certain thing and we perceive that as if we are living in 3+1 dimensional theory with gravity, because it's mathematically equivalent. We have 1-to-1 map. Okay? So the true, or at least one formulation of quantum gravity is one less dimension than you naively fears. And that's the theory without gravity. Okay? Because otherwise you could go to one more holography to one less dimension, one less dimension, one less dimension. You can eventually go to 0 dimension. That's not the case. D+1 dimensional theory with gravity is equivalent with the D-dimensional theory without gravity. What this is to do with the black hole? Now this tells you that the black hole in fact does not lose information, because you can do experiment around the center of this antidocity. You form black hole by colliding something in black hole and then evaporating to Hawking radiation. You can just do all these things around the center of the antidocity, and at short distance, curvature doesn't matter. Einstein told us that at short distance things look like a flat space. You don't have to worry about the curvature. And then everything happens inside antidocity. You can map this to some theory at the boundary, theory without gravity. In particular, in this case, it's something called conformal field theory, a special class of quantum field theory. We know that theory is unitary. Okay? It's because of usual theory without any gravity. It's just literally standard theory we know and love. Okay? So that means that black hole evolution had to be unitary, whatever that mechanism is. Okay? So that's the clue holography gives us. So if you, at the quantum level, so the black hole must be behaving like that. Namely, black hole emit Hawking radiation, but black hole has a huge gravity, so it traps a certain Hawking radiation. Yeah? So it's just the black hole carries the Hawking cloud around it. Yeah? And this cloud is almost thermalized because it's bouncing back and forth. And this cloud temperature become higher and higher and higher as you approach the black hole horizon surface because of blue shift again. Yeah? So gravitational redshift, blue shift effect makes the temperature is higher and higher and higher. And at some point, it reaches string scale where the space-time picture breaks down. Okay? That's the structure of the quantum black hole as viewed from exterior. So what happens if you drop the object to this at the quantum level? The holography suggests that material, okay, it just drops in, and at some point it reaches locally feels the temperature of the string, so it dissolves the material, and it's just distribute over horizon surface, and then that surface emit horizon, Hawking radiation at the end. So it's like this, going to and absorb it and coming back. That's pretty much the same physics as just the surface of regular material. If you send in something, it just dissolves into it, okay, just a fireball, and then that radiates the black body radiation and then come back. So this horizon surface actually looks like a material surface. It actually absorbs things in finite time at the quantum level, okay? And then it just emits back later. No problem. It's completely unitary. But then, what about the interior? Okay, again, if you take quantum mechanics and unitarity to be correct, and this picture, unitarity, no problem. You have some surface. Horizon looks like a real surface. Then, of course, no issue, okay, because it's a real surface. But then, are you saying that the interior doesn't exist? Okay? That's the question. Or alternatively, if you say that no, black hole interior must exist, namely general relativity prediction must be correct. That's the one we have. Okay? So then the interior is there, but then Hawking's analysis says that the information must lose. Okay? The Hawking radiation must not contain the information about the initial state. What was wrong with Hawking's analysis? Again, this seems to be a tension between quantum mechanics or unitarity, but then interior doesn't seem to exist. That means general relativity seems to be wrong. Or if you take a general relativity interior, then information seems to be lost. Quantum mechanical unitarity doesn't seem to apply. Okay? And this is not necessary at the Planck length physics, at least a priori. So this can happen at long range thing. That's what I meant at the introductory slide. Yeah. So and now I switch a bit gear and then go into recent progress about this issue. And these, I will tell you two recent progress coming from both sides, either the side of general relativity or side of quantum mechanics. And you will see in the end that these two approach looks completely different in an intermediate step, but the final answer to be the same. Dramatically, it gives a whole completely same physical answer to any physical questions you ask in a very subtle way. Okay. That's beginning of my real talk in a sense. That's a reason. Okay, so now let's start from general relativity's point of view. Namely, you have both interior and exterior of the black hole. And I have to explain one figure. This is only one important figure. It's called Penrose diagram. Okay? And this in this diagram, time is in the vertical direction and space is in horizontal direction. Okay? And you write the diagram. This is just the rule to write the diagram. The rule is that the light rays goes like 45 degrees. Okay? So that's the only rule of the diagram. According to this rule, following this rule, the black hole is written like this. This sky blue region is inside the black hole, and this dotted thing is a horizon. The reason is because light goes like 45 degrees. Inside this sky region, any light can hit the singularity. Okay, you can't go, this is a asymptotic region. You can't go in asymptotic region. And any material has to be slower than light, means that it must be more vertical than this 45 degrees. So anything, nothing can escape from this sky blue region. That's the interior, okay? Because it hit the singularity. This is a rule to draw the diagram. You have any question about this diagram? Probably better to write in the chat now, and then I can go more, but this is the interior region, okay? So the meaning that I have both exterior and interior means that equal time slice, I take like this, okay? And then quantum state exists. Quantum state is on this time T1, and then after black hole evaporate, it's T2, okay? So that's the description. So I started from general relativity, or called global spacetime. Okay? Black hole has interior and then also exterior, okay? Because in T1, it's slicing both inside and then outside. But what we recently started running is that this kind of description is hugely redundant. One way to view is that if you take this slice in certain way, which is consistent with general relativity, you see that this volume can be even arbitrarily large, despite the fact the area is finite. Keeping this area finite, you can cleverly slice it in such a way that the volume inside the black hole, like this portion, is huge. Okay? Then it looks like a completely at odds with the Bekenstein-Hawking entropy, because if volume is huge, then you can excite the material here or there and there. The number of possible configuration is like a huge, it goes like a volume, which is even not bounded by the area. And yet, Bekenstein-Hawking entropy says that the number of independent configuration is equally just the area, which is a finite quantity. So what's going on? What's going on is that this is a result of quantum gravity. In a semi-classical gravity, that's kind of patchwork, what I meant patchwork. And if you have a big volume, then you can have a material or object here or there, or many other places. Okay? That's all independent, clearly, because it's a different state. And in fact, in quantum field theory on curved space, it's called the semi-classical gravity, these different configuration is treated as orthogonal. But in quantum gravity, that's actually not the case. If you include the non-potential effect of quantum gravity, that's why, of course, it cannot be captured and semi-classical. Then, in fact, these different states actually have small, tiny overlap. E to the minus S entropy, which was huge, as I discussed, over 2. It's a tiny overlap is there. So therefore, if you think about the matrix in a bracket space, then this has small non-diagonal, off-diagonal elements. And if you diagonalize it, only e to the s is the state has a positive norm. Everything else is 0, 0, 0. Okay. That's why what we naively think it's a huge volume is a fake. It's not all independent. You can check this from the other side as well. Maybe, I don't know, I may not have time to explain these things. But if you think about e to the s independent states, you start from e to the s side. If you have e to the s independent state, generic state has a coefficient of 1 over square root e to the s, right? I mean, if you take a square and take a sum, and this is generic state. If you think about the inner product of these two generic states, it's like this. Each one of them is 1 over square root e to the s, 1 over square root e to the s. So the size is 1 over e to the s. And if you take a sum of e to the s, but the phase is random. So you have only square root of e to the s, okay, times e to the minus s. So this is a tiny overlap. If s is huge, you have huge amount of approximately orthogonal states, much more than e to the s. It's actually e to the s. Okay? So that's why it looks like orthogonal, and that's what we have been doing at the level of semi-classical gravity, which is hugely redundant. And this redundant, it would be the key, okay, to address unitarity Hawking information problem. So now in this language, what's the Hawking radiation unitarity issue is? If we trust the Hawking's calculation, Hawking's radiation can be viewed as creating pair of particles around the horizon in such a way that the one pair falls into the black hole inside the horizon. The other one is emitted as a Hawking radiation. Okay? So if that's the case, as time passes, entanglement entropy of this exterior of the black hole keep increasing monotonically. Okay? This is entropy of the radiation. Entropy, in this case, is essentially just the number of EPR particle existing in the Hawking radiation whose partner is not on R, yes, on the complement of R. Yes? So you keep producing EPR pair, and only one side of the pair is keep being emitted. So that increase the number of EPR pairs shared between this radiation and the complement, R bar. So it's keep increasing and goes and goes and goes and goes up. That's the Hawking result, which is a more mathematical way of saying information is lost. Okay, and you can compute this quantity. It's more precisely called von Neumann entropy. Is if you compute the states of R called density matrix of R, rho R, obtained by tracing the complement of R, and then take this combination, that gives essentially this number of EPR particles in R whose partners are in R bar. Okay? But if the things black hole evolution is unitary, then what happens? If the unitary, namely information is preserved, then initial state, say, consider initial state is pure state and you just collapse it, and the black hole emits the Hawking radiation, but the final state does not have any gravity, any black hole because it's completely evaporated. So there's no EPR partner whose EPR particle whose partner is not on R. You can't think about this because it's R is everything. So there is no EPR pair whose partner is not on radiation. Everything is radiation. So entanglement must be within R. So that means that the number of EPR pair of R and something else should decrease and goes to 0 because there is no something else after evaporation. So this is the curve which is predicted in unitary theories. Okay, and this curve is worked out by Don Page in around 93. It's called Page curve. You may have heard in recent programs. So the problem of quantum information preservation in this picture of the global spacetime. So existence of material is obvious because I started from there. But then to see the unitarity of the process, and you have to get this curve, okay, rather than Hawking's curve. So that's the issue. And the major breakthrough happened in the past year or two, pioneered by our own Jeffrey Pennington. This is really a big stuff. Yeah? In fact, you can get a page curve, and in fact, we know how to get it now. So let's consider some, okay, it's a bit sketchy because the technology is kind of really technical, and which probably is not appropriate to do here. But let's imagine like here, the states, okay, defined in global spacetime, it goes both inside and outside, okay? And then to think about the state of outside, rho R, density matrix of R, you can get it by doing some Euclidean path integral. Okay? You go to the Euclidean space and do the path integral by keeping quantum field configuration on this R, because state corresponds to quantum field configuration in the path integral formalism. Remember, path integral formalism, everything is classical. You just have to just sum up with all possible paths, okay, for the fixed initial state and the final state. So you fix this field configuration and do the Euclidean path integral, that will give functional of this field configuration here and there. That's actually density matrix. Okay, it's something like coefficient of the brackets corresponding to field configuration F and G. Okay, so that's a little bit technical, but now you get this density matrix or state of only R, and then to get von Neumann entropy, which was defined in this way, rho log rho of the trace, and you can get in this tricky way. If you just first compute trace of rho to the n for arbitrary integer n, and then take a logarithm and then take a limit, right? Because log is essentially rho to the 1 plus epsilon. So you can take a limit, n goes to 1, and then this quantity will give von Neumann entropy. So good thing about that is that you don't have to take a matrix logarithm, log rho r. You just take a matrix rho r to the nth power and then take trace. After taking trace, it's just number, and take a log, and then take a limit, and you can get von Neumann entropy. Okay? So how to compute this? Let's think about this n equal 2 case. Let's try to first compute the trace rho to the 2, rho square. You can do the similarly, trace rho to cube, and so on. Okay? So naively, this is a rho. So you can give 2 of those Euclidean slice. And then you stitch in certain way. If you go to branch cut, if you go to here and then go there, and if you go to here and then go there, that's representing this is not, it's rho square. And then you compute this, and similarly, n equals 3 case, 3 seats, and 4 seats, naive, trace rho square, trace rho cube, trace rho to the 4th, great. And then, and after doing this limit, in fact, you reproduce Hawking's result completely. And what Jeff and the others noticed is that that's not it. Because in a theory of gravity, a lot of all possible configuration has to be included in path integral. Once you consider rho square, in fact, you have this configuration in which wormhole is connecting these 2 seats. That's completely consistent, and it's a dominant saddle in certain situation. But in a regular regime, this thing, because of a higher topology, it's exponentially suppressed. So it's a non-potable effect. That's why you didn't see in the usual patchwork in Hawking's things. And if you include this, in fact, you get the page count. Perfect. So the mistake of Hawking in this language is that he did not include this non-potable effect called replica or wormhole, because you replicate it to compute the rho to the some power, and then you have wormhole connecting to different sheets. Inclusion of that was a key to get this. Okay, so what makes black hole radiation to be unitary is non-potable gravitational effect. Shocking thing was that we didn't have to know the full theory of quantum gravity. You can still take appropriate patchwork is enough if you do it carefully enough and then to reproduce this page curve. Okay, so what's happening here? More physically, what's happening is dramatic. So if you have a Hawking radiation emitted, at later, okay, Hawking pair is created. Okay, remember Hawking radiation can be viewed as one particle just falling in, the other coming up, coming from the horizon. But in order for this final state to be entangled among radiation, and these things have to be entangled with the earlier radiation. Okay? That's why if you take a time and time type, all the outgoing radiation is entanglement by themselves. But this says that these two are not independent, yeah? Because this guy is entangled with this red guy, but it's also entangled with that guy. It's not possible. It's entangled with what? So the only logical answer is that this red and this red, which one is an interior of the black hole, the other is an exterior. It looks totally different mode. It's actually the same thing. Okay, that's the example of redundancy I also talk about at the beginning of this presentation. So as suggested earlier by some others, including Matusera and Saskin, and it's independent, not independent. In fact, that's needed if Hawking radiation contains any information about infolding object at all. Then if you take a global space-time picture, and on this spatial slice, and then initial information exists in Hawking radiation and the object itself. So information is completely copied, which is prohibited by quantum mechanics. And this is consistent because of causality, cleverly, because if you're falling in, you can see only this guy. You cannot see this. And if you're outside, you can see Hawking radiation, but cannot see the interior by definition of the horizon. So it's not, no inconsistency happens because with causal structure of general relativity. So summarizing, we learned that if you start from global space-time, namely space-time with interior, something predicted by general relativity, then you may think, according to Hawking's argument, that information is lost. But it's not. If you carefully include non-particle effect of gravity called replica wormhole, and then in fact you recover the unitarity. Yes, that's recent progress one. Okay. And Jeff Pennington is a superstar in this. Okay. So now let's talk about the recent progress two, which is the approach I was taking, among others. So now start from some holographic or manifestly unitary view. Okay, we learned that from exterior's point of view at the quantum level, if you just throw in object, because of this Hawking crowd, and the crowd is blue shifted, and to have a string temperature around the horizon, it just simply dissolved into this something called stretched horizon, namely the Hawking crowd layer, which has a temperature of string scale. So that's why it's everything is like a string physics and that everything is dissolved. And this Hawking crowd region is called zone. That's just the name, zone and stretch horizon. So if object falls in, it falling in the zone and then dissolved into the stretch horizon and later come back as, okay? And no issue of information problem because information is just distributed over the horizon and then the radiation comes from horizon. So literally information flow is like these arrows. Okay? But we could achieve this because we did not consider interior. Okay? Because this is a material surface like, horizon is a material surface like, that's why we could claim that it's just easily a unitary. But then the question is that the interior actually not there? And the key features, actually interior is there in certain sense. The key features is the following two features. That's actually defining characteristic of black hole in this unitary, manifestly unitary view. Okay? In manifestly unitary view, and the black hole has huge energy entropy density. It's just E to the S. Okay? The level density of the states is huge. That's, you know, entropy is exponential, meaning that you have exponentially near degenerate states, which you can't given some finite time because of the uncertainty principle. Delta E, delta T is h bar. So in order to discriminate exponentially small gap, you need exponentially long time. But by the time you have exponentially long time, black hole is already evaporated. So you can't discriminate these black hole microstates. So which I call soft modes. Its modes exist, but you can't discriminate. Only big excitation can be discriminated. That's hard mode. Okay? So that's the one we describe as an object. This object is the excitation of this hard modes. And this soft mode is associated with this bunch of clouds. Okay? You can only say as a cloud. Okay? You cannot discriminate. It's so degenerate. Okay, that's the first thing I want to point out. The second thing is that now if you just things are dropped because of gravitational Blue shift. The temperature is over the string scale here. And then so the string dynamics become important near the surface. And while we don't know complete string theory yet, we know certain features because of these people, the analysis of these people. It's quantum chaotic. And in fact, the fast scrambling, namely essentially that this chaos is achieved right away, almost instantaneously in unit. And it's universal, meaning that this chaos acts on all the species. It acts on electron, it acts on photon, it acts on neutrino, it acts on dark matter, it acts on everything. So everything, its approach to the horizon, it's dissolved into the horizon, completely mixed up. And completely mixed up means that it becomes thermal state. Okay, so because of this string dynamics at the horizon, any object which is falling in feels complete thermal, okay, ultimate thermalization. Our usual thermalization is not. We say the sun's surface is thermalized and so on, but it may be thermalized in terms of electron and photon, but neutrino maybe not, right? Neutrino maybe just going through. No, this black hole, because of the huge Blue shift, okay, and it become locally, because of Blue shift, locally becomes string scale. Anything is summarized here, any object universally. Now, people knew in the 70s that let's think about some vacuum or Minkowski space. It's called nothing. It just goes on. This Minkowski vacuum can be described equivalently with some thermal states. If you see some this Minkowski vacuum from accelerated frame, if you are accelerating like this in this diagram of time and space, you're accelerating away. Any signal from this left side won't reach you. So you have actually horizon, even if you're just living in the vacuum space-time, okay? So you have approximate horizon just generated by your own motion of the acceleration. So this side never reaches, again, this is a light 45 degrees diagram, okay? So light goes 45, and any massive particle goes like more vertical. So this region never reaches. And if you rewrite the state just in terms of something you can actually see, then it looks like completely thermal state. So somehow vacuum looks like thermal state. This is called Unruh radiation, if you know it. If you're accelerated, you see the bath of the like space looks like it's thermal bath. Conversely, if you see that something is completely ultimately thermal, namely universally thermal, that means that actually you don't have anything. It's just smooth. This is really like an inverse Unruh effect. Because of this surface, its string effect is completely chaotic and completely fast scrambling, completely universal. Any quantum field theory is completely thermalized. That means that if you change the frame from accelerating to usual inertial in this case, or from external observer to falling observer, then it looks like nothing. It's pure empty, and you go through horizon. You don't feel horizon in that frame, and then the object feels that you were just throwing and then moving into the horizon without hitting anything. Okay? So this is how, in this unitary picture, the interior shows up. And this left and right shows up from actually, if you look at this, and if you throw in object is a hard mode. Okay? And then the picture is this soft modes respond to the hard mode, and then quasi-particle or collective phenomenon of these soft modes behaves like interior. That's the math. You can show that in math. So it's precisely this thermal state structure shows up in between hard and soft. Remember, this feature of complete thermality came because of string dynamics. It's not in the usual material surface. Okay, it thermalizes some object, some particle, but not the other. Then, of course, you don't see this phenomenon. So that's the difference between black hole and the regular surface. Okay? So black hole is unique. And moreover, I'm wrapping up in a minute. And moreover, at late time, because black hole is entangled with the Hawking radiation, because keep emitting Hawking radiation, this quasi-particle or coherent phenomenon, which is a partner of the hard mode, involves radiation emitted earlier. So Hawking radiation emitted earlier is not independent with the interior. That's exactly the same conclusion as recent progress 1 view, which started from global spacetime. And then you recovered unitarity by replica wormhole. Here, I started from unitarity and then recovered the interior as collective phenomenon of these soft modes and so on. So the description looks completely different. And yet, if you ask any physical questions, you get the same answer about the physics. So what's the structure of quantum gravity we learned from this analysis? So yes, the conflict was between general relativity and quantum mechanics. And in one description, Jeff was pioneer that you start from manifestly global space-time point of view. You have black hole interior, of course, because I started from general relativistic space. Black hole has both exterior and interior, both, of course. But then Hawking's analysis would say that information is lost, but it's not. If you include replica wormhole, it's actually unitary. And I started from manifested unitary by construction. Okay? It's just a holography, so it's just unitary, and viewed from exterior, that's more natural to be unitary. You don't care Hawking's analysis because no interior at this point. But then interior shows up only as a collective phenomenon. Okay? And similarly to this progress 1 case, to argue this collective phenomenon, you don't need the details of quantum gravity. Only thing you know is that that's chaotic, it's fast scrambling, it's universal. That's kind of like rough features of quantum gravity is enough to conclude that the black hole actually must have interior, in the sense that if you yourself are falling in, then you feel, you perceive that there's nothing at the horizon and you have interior space-time. And you can ask a lot of different questions in these two frameworks, different questions. And the way these questions are answered, I won't go through. The way these questions are answered in two frameworks is different, but the conclusions are again same. Okay? So this is like a completely two different formulation of quantum mechanics, like path integral and operator formalism. It looks very different, but the answer seems to be unique. And we learned that only one of the general relativity or quantum mechanics can be made manifest. The other, whichever this is arising as a very subtle effect. That's why it was so difficult to make quantum mechanics and general relativity to unite. And ultimately, the reason behind this phenomenon is, or existence of completely different two descriptions, in the existence of black hole. By the way, without black hole, these two descriptions are almost same. Okay? In the black hole, it starts deviating, and it's very differently looking. There's these very different looking. The origin of this a different looking description of the same physics is actually redundancy of quantum gravity. In gravity, we already know huge redundancy called general covariance, namely to describe the same object. Like here, you can say, oh, this object is a 1, 1, if you take an XY coordinate. But you could say, oh, no, this object is a square root 2 pi over 4 if you take the R Taylor coordinates, right? It's a coordinate. If you change a coordinate, it looks like a completely different location in terms of description, but it's actually same. So only physical thing is something invariant under this coordinate recoordinatization. That we knew. Yeah? General relativity also has that. In particular, in GR, you can even do arbitrary slicing of the space and time. Okay? But you have even bigger, much bigger actually redundancy. And at non-particle level, single universe, for example, can split into two. This is allowed. Topology can change through non-particle process. And in that case, depending on slice, okay, or coordinatization, it may look like one universe or two universes. And those things are actually talking about the same states. Okay? So it looks so different in our usual thing. It's actually same. Because of that, it looks completely different descriptions and actually saying the same thing, is describing the same system of black hole. Okay, that's what we are learning, and those things were discussed by these guys mostly. And the point is that and it turned out to be in the existence of black hole, only one of the pillars can be made manifest, although both exist, because simply the other looks non-manifest, and you need to include the subtle effect to see it. Okay? So let's conclude my talk. So what we keep learning about quantum gravity is it's surprising in some sense, and hindsight, it might sounds like it's, oh, of course, this kind of phenomenon we saw in physics in many places, path integral and operator formalism, gauge fixing of the Yang-Mills theory, unitary gauge, and then Lorentz gauge. But again, in a bigger scale, the same thing is happening. So and if you think about black hole conundrum carefully, we start seeing the structure of quantum gravity, that quantum mechanics, general relativity, apparently only one of them can be made fully manifest, but whichever you choose to be manifest, the others seem to appear from subtle considerations, a non-potable replica wormhole or universal thermalizations, and so on. So the theory actually has both to be consistent with the both quantum mechanics and general relativity. Okay, so that's what we keep learning. And interesting thing, and this is very recent, and an interesting thing is that by doing this kind of study, quantum gravity issue, but quantum gravity looks like a very special field. It's not. Clearly, we are studying black holes and gravity and so on. It's connected with the high energy physics and astrophysics. I mean, in the end, the member of the particle theory group. Okay? And I didn't discuss too much, but in fact, through holography, any geometric object is mapped to quantum information quantities, which I just mentioned. And it's crucial to understand the property of these quantum information thing, how these quantum information things kind of make space-time emerges. Without understanding it, you cannot go deeper than superficial level. So quantum information science was needed to do this. And the dynamics we saw was chaos and fast scrambling, those things. Those physics is pretty much the ones studied by many body physics, as a many body physics in condensed matter and AMO physicists. So we have to, we are kind of non-experts of these things. We have to be kind of consulting these people as well, and so on. So it touches on a lot of different physics across very different subfields. And so far, I haven't seen the biophysics here, but maybe who knows, maybe at some point biophysics may be needed too. So this is a fun part that this problem is really requiring full theoretical physics, and which are traditionally classified into different subfields. And perhaps even more interesting thing for this audience is that indeed Berkeley is a leader in this effort. And in fact, we have some consortiums between Berkeley, Stanford, Duke, Brandeis, Brookhaven, led by Berkeley, and with in particular Raphael Busso is the head of this collaboration, which is called GeoFlow, supported by the Department of Energy, and our department, the faculty members in our department joining in this collaboration. So these are the names. As you see, it's not just a particle theorist, it's only two, in fact. Oh, Jeffrey's also these members, but it's quantum information people, condensed matter people, AMO people. So this and experimentalists of the quantum computing. So this is really fun time that to pursue this theoretical endeavor of quantum gravity. That's it. Thank you.
Okay, thank you very much, Yasunori, for that great talk. I'm afraid we're basically out of time. I see one question in the chat box from Chris McKee, which I'll just quickly read. Since we don't yet have a theory of quantum gravity, how could Maldacena show that quantum gravity in d+1 dimensions is equivalent to a non-gravitational theory in d dimensions?
Thank you. It's great. And what Maldacena showed was, in fact, the string theory on asymptotic area space is like a spectrum and then certain everything he could compute is the same as non-gravitational super Yang-Mills L equal for particular theory. So because both sides is particular theory, like type 2B string and then compacted on certain thing, ADS5 cross S5, very particular theory. In string theory, you can compute things and every computation matches. Boom. And then now you can start deforming both sides and assume that the corresponding persists. And then all circumstantial evidence says that it still persists. So that's the way it happened.
Is there time for an oral question?
Yes.
Oh, yeah.
Okay, so I'm so glad that you have resolved this paradox. And I'm really happy about that. But the same paradox appears in all parts of physics. For example, we have quantum mechanics says that you never have more entropy, you have the same amount, but If you have physical chemistry, they're constantly seeing that things increase in entropy. For example, you could stir an egg, and quantum mechanically, the entropy is not supposed to change. And yet any sensible person says, yes, you stirred the egg, it's all messed up. Okay. It has more entropy.
Okay, so let me answer. So first of all, the solution, some people say this is not the complete solution because we don't have a microscopic dynamics. We start seeing how things are solved. It's just this is a disclaimer that some people think this is, roughly it, but it's not complete in a sense that we have microscopic theory of gravity. But that's not to answer to your question. Your question is like entropy. You have two concepts of entropy. One entropy is something I use here. It's called von Neumann entropy. So if you have quantum state to be pure, okay, it's not a probabilistic ensemble, then entropy calculated by low log rho is really doesn't increase. Okay, it's called just the Liouville theorem. And yet entropy after you coarse-grain, that's called thermodynamic entropy, increases. There's no like conflict between these two things. It's just simply the name entropy is used for two different concepts because it's related, so it's not completely crazy. So that's why it looks like, oh, entropy is increasing in usual thermodynamic entropy increasing, but the fundamental entropy doesn't increase at the fundamental level of quantum mechanics. There's no inconsistency between the two because thermodynamic entropy arises after coarse-graining.
Okay, thanks.
Okay, thank you.
What's the other entropy called?
Oh, von Neumann entropy, or you could say fundamental entropy. Yeah.
Oh, fundamental. Okay,
yeah.
thanks.